Continuing my video series about designing PMSM motor drive. This is the drive I'm designing, and today I will continue connecting the pins of this DRV8302 chip and going over the remaining pins that I've not connected yet. In the previous videos you can find all the details of the design of all parts of this circuit. I'll bring up the datasheet of the DRV chip and I'll look at the pin descriptions here. So our current warning pin, I think it's a digital output. This output is open drain with external pull-up resistor required. On the schematic here they put 10 kilo ohm resistor and then they just connect it to GPIO. So we have power good and our current and fault. All of these pins are going to be connected to GPIOs, and they will be, for now I will just name them with labels, but I won't connect them yet because I'll wait until I have connected the more important parts, such as the key interfaces for controlling the inverter and things like USB ports and other interfaces. And then I'll connect all of the other GPIO pins to whatever pins are available on the STM32. So let's use a 10 kilo ohm resistor here and another one right beside it and yet another one there. And then I can move this a little bit so that we don't get an overlap there. Then I can move the label there, and this would be OC31, and this will go here. I think power good is actually for the buck regulator. Let me check whether this is, I'm curious if this is for the 5 volt or for the input supply. With external pull-up asserts low if buck output voltage is low due to thermal shutdown, drop out over voltage or enable buck shutdown. So we don't need that thing. We can right away remove one of the resistors, and we can connect only the overcurrent warning, and then I'll connect this one as well. And I'm putting numbers like 1 after the name of the pin, because I'm also going to have another chip that's going to have a label that will have number 2 in the name. So all of the labels that I put on this motor control schematic that are not supposed to be connected together, they're going to have unique names. Mode selection for PWM input configuration. Okay. This is unnecessary. We don't need to support three lane PWM mode, because we're going to be generating both the negative and the positive PWM, and we're actually not even going to be using the dead time control. And the mode selection for overcurrent protection, the gate driver will operate in cycle by cycle, or it will shut down the channel which detected an overcurrent event. So this is good to have connected to the MCU. The gain adjustments are done by supplying either high or low on this gain input. And this is good to have connected to the MCU as well. Overcurrent threshold is this is set using a voltage divider, or in our case we could set it using the digital to analog converter, or using a potentiometer. I'm going to leave this pin, I think, unconnected for now, and I'll decide later if I'm going to use an extra digital potentiometer connected over I2C to set this overcurrent threshold, or if I'm going to be using the digital to analog converter on the STM32. I would prefer using a digital potentiometer because the chips that I've been looking at, they can support saving the resistance values. So essentially, the moment you power on the chip, you don't need to do any other configuration. You're going to have the presets automatically restored. So that's one less thing to worry about. The downside is that requires an extra chip, unless I have some channels that are free on another digital potentiometer chip that is used elsewhere on the schematic. So therefore, I will just leave this pin unconnected for now. The DC calibration, when it's high, the device shorts input of shunt amplifiers and disconnects loads. DC offset calibration can be done through external microcontroller. This is DC offset calibration for the output pins here. What we want to do is adjust the DC to measure. Actually, what we want to do is to measure the level on these inputs when we set the DC calibration to high, and then we would like to use that value as the 0 point for the currents. So connecting this to a microcontroller is a good idea. GVDD is internal gate driver voltage regulator. There should be a capacitor there, and the capacitance that they use is 2.2 microfarads. Let's use one of these. And now we have CP1 and CP2, and that is charge pump pin. Ceramic capacitor should be used between CP1 and CP2. And what they use is a 22 nanofarad capacitor. Do I have anything close to that? Let's see. Okay, that was the history. So look here. Let's see. So 6.8 nanofarads. ideally I want to use a 402 component here, so I don't want to take any parts that are 0603. Not anymore, at least. I have moved away from using 603 parts. And what would be the voltage rating of this capacitor? Let's check the datasheet and see what the voltage rating is. So the charge pump is connected to the main supply voltage, which can be up to 60 volts. So I'm curious whether this capacitor needs to have that rating as well. Okay. Oh, this was nice. So 20% ceramic, rated for PVDD1. Right, okay. So this has to be 63 volts, at least. I'll search for or actually I'll search for the capacitance, and then I'll choose the packaging after I've picked the voltage, because it could very well be that these capacitors could be a little bit larger due to the high voltage. And I'll click the in stock, and I'll choose this 0.22, 63 volts, and everything above that. Let's see. There we go. And surface mounted. 361 alternatives, and they seem to be 0603 or higher. So it is actually highly unlikely that I'll be able to find anything smaller. Okay. Since I'm not using the 68, what was it, like 6.8 nanofarad or whatever, I'm not using that capacitor anywhere else on this board. So I might as well just add the 0.022 microfarad capacitor and use this one on the board. And also add it to my library. Just to follow the reference schematic as much as possible, but adjusting it to the inputs of the STM32. This looks like the perfect alternative. And now we have the 603. Let's see. I think, yeah, I can copy this one. Copy this one, and it's going to be 0.022 F, 100 volts. good. Close this one and update my script. Run my script again to update the components. And now I should be able to add this capacitor and have all the fields set. Zero 0.603 and yeah, and the footprint is correct and the description is correct. This will go here. I can place it like this. So then we have the enable gate input. This input, let's see what it does. They have the enable gate just connected directly to GPIO pins. Okay, we're going to be using the AND gate to reset any faults on this chip, and let's see. Okay. Okay, that's good to know. So if this pulse is longer than 20 microseconds, then you're gonna have an issue. Okay. Yeah, although that's not an issue, it's very easy to toggle the pin. We'll just need to disable interrupts and do a quick toggle. Or use a timer. I think actually this pin should actually probably be connected to some sort of timer output, and then we can just set precise length of this pulse and ensure that it's less than 10 microseconds. Okay, this would be AND gate. And then we have the inputs for the MOSFET driver. The high and the low and the high and the low and the high and the low, and they're all going to be moved a little bit to the side to allow for the designator of that capacitor to exist without being obscured by labels. So this would be inlet A, and this one would be in HB1. So high input of the gate stage B on the gate driver number 1 in LB1, and in HC1 and in LC1. And the ref pin, where do we connect the ref pin? easier to find. I want to find the table that outlines all of the pins. And also I'm just going to check the schematic. So ref goes to... Interesting. I guess I still need to find out what it does. Let's see. Come on. I think it was somewhere in the beginning. Start from the beginning. So starting from the beginning. There we go. So ref is a reference voltage to set output of shunt amplifiers with a bias voltage. Let's see. Equals to half of the voltage on this pin. Right. So can we adjust the bias? I thought the bias was just let's see, what is the bias? Connect to ground or capacitor to ground. Okay. Amplifiers with the bias voltage. I'm not really sure what they mean, and they specify this as an input, which is very strange. This is very, very weird. And they call it amplifiers. What language is that? Okay, I need to find out what this ref pin actually does, because this is really, really not clear. External voltage reference for current shunt amplifiers. Like everything in the datasheet just screams that this is supposed to be connected to a voltage reference, yet at the same time they say it's supposed to be connected to ADC. Maybe it should be connected to both. Oh. So VREF I think is another input. Didn't they have a VREF somewhere? Okay. So what does it actually do? This is very strange. Am I supposed to connect any reference there, or what am I supposed to do? Okay. Maybe I can figure out what this does. Okay, so VREF is apparently the voltage on this pin. So S1 would be for the gain. So if we use, let's see. Oh, let's see here. This is interesting. So the current shunt amplifiers have two gain settings. These are 10 and 40, and provide an output offset up to 3 volts to support bidirectional current sensing. The offset is set to half the voltage on the reference pin. So everything that I've read so far tells me that ref pin should be connected to 3.3 volt supply. Or actually, it should be connected to the analog 3.3 volt supply. DC calibration is enabled. The device shorts the MOSFET, does not do any switching, and to produce the potential noise impact, to reduce, okay. The output of current shunt amplifier can be calculated as Vref and G is the gain, which would be 10 in our case, and SNX minus SNP. So negative input would be around 165 millivolts, and then when the current is high enough, and then the positive will be just connected to ground. So we're going to be amplifying the difference between the positive and the negative here. And so we have the output will be when the current is 0. Okay, let's say there is no current flowing through the resistor. Then the voltage difference here is going to be 0. So then we will have Vref divided by 2. If the current is flowing, we would actually have a value that is lower than, should this be plus? Interesting. And if we have reverse current flowing, then we'll have a value that is above half of the reference voltage. I'm beginning to get a little bit suspicious of this datasheet and of the correctness of anything to do with the ref pin. The only thing that I'm pretty sure about right now is that this pin is supposed to be connected to 3.3 volts. I'll connect it to VDD-A. I think it's called VDD-A. What did I call the ADC? VDD303 ref. Okay. So I'll connect this for now to the VDD303 ref. And that, if it does work the way I think it works, which I'm gonna do a little bit more research on, then this is the correct connection, because the ADC is going to operate from this ref voltage. So anything that we read here is supposed to be referenced to this VDD ref. And if I do this in this manner, then I should also connect a capacitor here, which is getting a little weird, because this deviates quite a lot from the reference schematic. So this capacitor will be placed very close to the ref pin to filter out any possible noise that arrives on this trace going to this ref pin. I should ideally use a little bit larger tantalum capacitor or something, but I'll leave it like this for now, because I need to really figure out what is going on with this ref pin. Okay, so we have a few labels here that are all going to be connected to the microcontroller. But for now I will not connect them to any specific pins, and instead do that in one of the coming videos. But what I can do now is just copy this over. Let's see. I'll duplicate this schematic and I'll create the second driver. And it doesn't really matter that that I do it like this. It can be a little bit cumbersome to add or remove components, and I'll have to do it on both schematics at the same time. But with regards to labels, it doesn't really add any extra work, because I still have to rename, I still have to reconnect the labels that will go to the microcontroller. I have to put number 2 on each one of these labels. So I'm gonna go ahead and change these labels to number 2, and this is something that I don't think is a lot of fun to watch, so I'm gonna stop this video and I'll continue the design of this schematic in the next video in this series. Thanks for watching and have a good day.